we will do relativistic quantum field theory. You might say, oh my God, you don't have respect for the condensed matter people. I do, trust me. And hopefully towards the end of the lecture, not today's lecture, at some point you learn how to raise the relativistic part. Okay? So quantum field theory, so this is just some build up. Quantum field theory in this sense, okay, relativist quantum field theory, meaning this framework or language works in a system that has something moves super fast and super small. Okay? So quantum field theory is broadly a synthesis of a special relativity and then quantum mechanics. And it's hard to, by the way, put them together, as we will explore in the first few weeks or so. And so we will spend some time how to think about these two concepts. So in this part, the key concepts, what is better? So key concepts, in the category of quantum mechanics is something like quantization, meaning how you have some classical description of a classical system, how you pass on to the quantum version. Okay, and then there's a key concept known as unitarity. Okay, so this is related to probability conservation. And then there's a concept as something as absence of absence of none becomes actually existence. Negative norm space in your Hilbert space. Okay, so negative norm space. So this is needed in order to have well-defined notion of even probability at all. So we will be doing something like this. Probably already are very familiar with. In the category of special relativity, we will talk about concurrent variance. So we will today discuss concurrent variance, and as a subset, we will also discuss Lorentz variance or Lorentz translations. Okay. Making sure this doesn't fly. Does this help? Okay. And then we will start jumping in and thinking about the notion of the locality and causality. Locality says that what I'm doing here cannot affect what people in Switzerland think right now. Right? So you shouldn't change what that person is about to do. Causality is a deeply related locality. Right? You cannot modify what happened in the past. This is deeply related. Let me see. So we will explore this, and then we'll spend some time how to put them together. Now, quantum field theory is a language. So here, whether you have a relativity or not, but again, we will spend most of the time thinking about quantum field theory of relativity, relativistic invariance. So this is a principal language in many fields, so including, say, particle physics. For instance, Standard model is constructed using this language, and all kind of beyond Standard model is also constructed based on this. Also, this is a principal framework for formal theory, such as formal quantum field theory or gravity. So there are many different kinds of quantum field theory names you will hear. For instance, you will hear supersymmetric, nothing we will cover at all. Supersymmetric quantum field theory, where now, in addition to the relativity, for instance, you demand extra structure called the supersymmetry, or formal field theory, or logical quantum field theory. Okay, so there are other mathematical structure you demand or you can get rid of out of this structure. And this is obviously also a core language used in condensed matter physics. So here, sometimes you may not need the full relativity, and sometimes this may not even look like a completely continuum role. So here, you may be dealing with lattice field theory. Okay, and a very popular subject is topological phases matter. There are many, and also this appears in statistical physics. So, for instance, if you want to deal with a system that you can heat it up to a certain finite temperature, right? Or you can want to deal with a system with a super high density, right? There, you also need a language. So there, it's called either statistical field theory or many-body field theory, and so on and so forth. Okay? So this is the core language, and the goal of this lecture, this class, and the companion lecture next semester is to build up the general machineries and understand the concepts and then learn how to compute things. Okay, so that's overall overarching motivation. Okay, good. So unless there is any question at this point, now let's actually play with this. Okay. Let's start playing with adding a special relativity to quantum mechanics, or adding quantum mechanics to special relativity. So I will spend just like 5 to 10 minutes why you should expect something non-trivial will happen. Okay, and then in the rest of the lecture today, I'll just focus on machineries of special relativity first, and then we will play further. So here the question or test that we want to think about is how we might add a special relativity to quantum mechanics. In other words, I want to describe a particle, right? But it's not like a classical ball, like moving and slow enough and then big enough I can just keep track of it. Rather, I want to describe a particle whose size is very small, and then it moves super fast, right? So very small. So there you expect some certain quantum mechanical expectations. Very fast. So you expect a relativistic feature is important. So by this we mean, for instance, I want to consider, say, energy scale of a system or particle which exceed, for instance, the mass scale, if you wish, the square states. Okay. And then I want to have a quantum mechanical description of a such particle. What could go wrong? What could be subtlety if I just demand of doing this? Well, this at least tell you one thing. First, if we instead, let's just consider if energy were smaller than m, and if total energy, this can be, you might say, what am I doing here, right? What am I even doing here? So let's just be careful. So here I mean that. Here I mean let's consider regime where total energy is much larger than that. That's what I mean. So in this regime, if the kinetic energy is less than m, obviously we know we can reliably use some unclassical description, non-relativistic description. And what it can happen is, for instance, if I had a particle with a mass, then go on, or even if I smash them together, they just deflect a little bit. The excess of kinetic energy is not large enough that they cannot do crazy fun things. So what do I mean by crazy fun things? Let's consider now a regime where total energy is much larger than that. Okay? Now, each of these particles have large enough energy that they can actually produce new particles that weren't exist before. So here's an example. So in the real world, you don't have to worry about it. But in real world, there's a particle called electron. And for deep reason that we will explore, there's also a particle called the positron. So this basically looks like this, except the fact that charge is opposite. There's also a particle called the muon. whose mass is much larger than that. Okay? So this guy, mass is roughly 0.5 MeV. Okay. At this point, you're okay to be upset or confused. Professor, what do you mean by the mass being MeV? I've never seen any idiotic people talking about that, right? Or not? I will clarify what I mean by this. But anyway, some mass. All I wanted to say is that this is much heavier than, say, 100 in bedroom. Okay? Much heavier. And again, for similar reason, deep reason for the existence of this particle called a positron, which is like a friend of this guy, there's also what's known as an anti-muon. So this is much heavier. So if I take two particles, electron and positron, say, and then if I smash them together at energy much larger than their mass, so much so that their energy even exceeds, say, the mass for the muon itself, which is much heavier guy, then when they collide, in principle, they cannot produce mu plus mu minus pair. Okay? Sort of mu state, which you didn't have in the initial state, can be popped out, for instance. More interesting can happen. So you send the electron positron. So my notation is that if I write this, I mean I'm smashing them together. Okay? Sometimes they can even produce just simply more of that. Because now they have a large enough energy to do so. So if you care about it, the relevant Feynman diagram, you might say, oh, Feynman diagram. I thought that this lecture is supposed to teach what that means. But for now, you just accept it. Obviously, we will build up. You just show that you smash them together. Then there's something funny going on. You don't have to know what that means. Okay? And then, so you can simply just produce more of it. Point is, you can just produce more of it. Now, one message that I'm trying to deliver here is that when you try to zoom into the super ultra relativistic regime, and then you want to have a quantum mechanical description of such event, you cannot just say that I want to describe the electron. Give me a description of the electron, relativistic, quantum mechanical. Don't ask me more. No, you have to take the responsibility of considering many particle phenomena. So in this region, almost necessarily, I will clarify why I say just almost. When you try to smash them together, you should be ready to talk about including many particle phenomena. Even the state which you did not expect to describe, they have to bring in this description as well. Okay? So that's the first aspect that I'm just trying to say. And you should have expected. So there's another way of saying the same phenomena. So we all know uncertainty principle. He says this, or he says this, right? So this is completely the quantum mechanical thing, right? That we learned. Now let's try to use this expression in the relativistic region. So relativistic region means that energy increases, right? So you keep increasing to this region. When that happens, then time scale for something to happen will go down. Okay, something happens faster and faster. So emerges. So when they do that, that means that the time scale or time uncertainty goes up. Okay? Something happens in extremely short period of time. But something happens fast. That means that uncertainty in energy goes up. So what this means is that during such a small period of time, the size of uncertainty in energy involved in that process becomes larger and larger and larger as you increase total energy. Which means that this process now knows how to borrow huge amount of energy out of the vacuum and use that, but but that event only borrow this much of energy only during that small period of time. Okay, I cannot just borrow the big energy long time. You can borrow and then do funny things. For instance, so starting from nothing, so this is my drawing of nothing, and then during small period of time, it can borrow energy out of the vacuum and create some massive particle. But it cannot do all very long time, so eventually you have to pay back. So this is the relativistic regime of certain quantum mechanical effect. And you see that even starting out of the vacuum, not even starting from certain initial state, literally out of the vacuum, you can still produce certain particles in multi-particles. Okay? So overall, this simple argument suggests that when we try to merge this together, which we will do it in a more sophisticated in a precise sense, then you should be open-minded and be ready to include many particle phenomena. And one of the very specific kind of many particle phenomena, and crucial, is known as antiparticle. So when you wanted to describe a physics of one particle state, say in quantum mechanics, particle in the shell, barrier, energy barrier, when you try to jack up the energy and then enter into the relativistic region, you should be ready to introduce a pair of the particle known as antiparticle. And we will see that without introducing that antiparticle, this cannot be merged into single thread. Okay? So that's where we are heading for a few weeks. Okay. So now I set up the notation, I set up the unit. Yes.
Can I ask why we should take care of the very short time scale? Because I don't know why we should consider that condition.
Okay, so you're questioning why this means that. Okay, suppose I have a two particle, and then I send in 2 meters per second, and then I started at 2 kilometers away. You know how long it's gonna take to meet? But suppose I take the same particle, again 2 kilometers away, I start increasing energy. It will move faster and faster and faster and faster. So as I increase the energy until I hit the full relativistic upper bound, which is speed of light, the time scale for the interaction to happen, something to happen, will decrease, right? It will happen faster and faster. So the interaction will happen in a short period of time. And since the overall time scale goes down, uncertainty with respect to that will also go down. And then during this uncertain time period, which overall goes down, what I'm saying is that you have a larger access to the energy depth you can borrow from the back, and which will automatically increase certain bubbles of particles that you never intended to describe. Okay, another question. Okay, so in this lecture, we'll use what is known as natural units. A unit completely natural to people like us, for which sometimes people may not like it. So special relativity, one key quantity is the speed of light, c. It's just a small c, okay? And this is one close. And then quantum mechanics part, there's this h bar or h, whichever way you like. This is a unit of angular momentum, which is 1. So this is natural unit, but then this has a consequence, right? Everything has a consequence, so let's learn that. So first of all, energy, roughly speaking, is mc squared, right? So when I write this expression, I just mean that in terms of unit. Okay, I don't mean the exact expression. Obviously, the exact expression being the square root, p squared, c squared, blah. But this is in terms of unit. Since we set that to be 1, that means that the dimension of energy is the same as the dimension of mass. So, therefore, we will be freely speaking that the mass of the electron, like I said, is 0.5. I said last previously, MeV. So in this sense, okay. So mass has the same unit as energy. Okay. not kilogram distance. Good. And then velocity is length over time. But since one of the example of a velocity is c, which I set to be 1, which means that in natural unit, length has the same unit as time. Okay? So basically, the distance is measured by how much time it takes given velocity in units of speed of light. Okay? So if it goes like speed of light, obviously velocity is 1, but it goes slower, velocity can be like 10 to the minus 3, whatever. But it is just a dimensionless number now. Okay? So in this unit, length take the same dimension as the time. Now, how about the uncertainty principle? So uncertainty principle says delta p, delta x is spatial. Not which is a dimension, which is 1. Which means that the dimension of length x is opposite to dimension of momentum. Well, momentum is mass times v, and the v carries no dimensions, which means that length has an inverse mass dimension. And you can use the same uncertainty principle, but not for energy and time. But we already established that because this relates the energy to the mass, length to the time, so basically you can keep going back and forth. But anyway, so energy now has inverse time dimension. So basically here, there's only one meaningful unit, right? What is the what is the size of either energy? Since I know the energy, I can tell the units of the mass, and the other two, length and time, is inverse of that. There's one kind of unit we just need to keep track. Okay? In that sense, it simplifies the discussion, or maybe create confusion. Okay, so that's unit that we're going to use in this picture.
Right, so can you represent the uncertainty principle in terms of math time?
So the question was, can I represent or express uncertainty principle in terms of mass? Yeah. So the answer is it can be given a circumstances. Suppose that we consider a system where there is a somewhat heavy particle, massive particle with a mass, where when we talk about the uncertainty in energy, the mass effect is very important, right? Then the uncertainty is controlled by, suppose we don't know precise measurement of the mass of the particle. Then it controls the uncertainty in energy. Uncertainty in the mass is the dominant effect in the uncertainty in the energy, for instance. So therefore, answer is depending on the physical situation and the system. This can be governed by the mass uncertainty, but it's not that the entire general formula of uncertainty principle it can be written as a mass uncertainty. So the second is not correct, but depending on the situation, it can be driven by the mass. So that's possible. Good. Any other question? Okay, so then let's do some more serious business. Now let me discuss some basics of let's talk about some basics of relativistic theory. So like I said, now today we will basically spend the rest of time to teach us the correct language to speak for SR part, special relativity part. Okay? Okay, so here, so the first thing, here, the first thing I want to say is background geometry of spacetime relevant for dealing with the special relativity. So the situation here is we don't treat spacetime itself as part of the dynamical entity. Rather, we assume that there's a fixed geometry of space and time, and then we imagine that some, super relativist quantum mechanical event happens. Okay, so space-time is not part of the dynamical object, like in the gravitational theory. Here, it is just background, and in particular for special relativity, so if this is K for you. So say this represents a 3+1 dimensional flat geometry where space 3 represents a space. Okay, space 3, and then there's a time. And this is flat in a way we can be more precise. But for now, it suffices to say that so I have a fixed geometry which is flat in a reasonable notion without introducing full machinery of the general relativity. And then this thing might have a coordinate. There's a 0th coordinate, 1, 2, 3, and then these 3 represent space, x, y, z direction if you wish. This is basically time. And such a flat geometry, flat space of time in 3+1 dimension is called Minkowski in Minkowski space and time. And obviously, just as a side comment, one can develop a quantum field theory not in the flat space and time, but in a curved space and time. That's possible. And one can dream of even getting a space-time geometry itself as an outcome of dynamical principles, such as a quantum gravity or string. So the object that I have just written down, this is an example of a 4 vector. Because it has a 4 component, but we have to be careful which ones are space, which ones are time. We will introduce a machinery to differentiate when it's necessary between the time and space, but at the same time, putting them together in a single frame. Another example of 4 vector that will come up quite often is a momentum 4 vector. Again, we will have a 4 component. We will discuss more and more. So the first entry, just like a time component, here time component is the energy, and then it has a 3 momentum. So this has a 3 component with it, like 3 Euclidean sets. Okay, so now, in order to actually talk about relativistic invariance, the next thing we introduce to deal with that geometry is metric. So notationally, we are going to use a notation for metric as this G object with 2 indices. By the way, this mu index, for some of you who are not quite familiar with it, this mu index is sometimes called the Lorentz index. This thing takes 0, 1, 2, 3 instead of a 1, 2, 3, 4. That's also okay, but we are using this way so that distinction between time component and the spatial component are more manifest. Okay, but some people may prefer instead. I'm just going to use mu 1, 2, 3, 4. That's also fine, and sometimes we actually do it. But in this lecture, we will keep this. And then I'm going to use these indices to label space and time index. Okay, this is a mu nu index versus mu nu alphabet, as you'll see here. Okay, so the metric, in principle, is a function of a point in the space and time. So at any point I can pick in this space-time geometry, the metric in a rough sense encode detailed geometry of that point. Okay, whether that's curved or not, and so on and so forth. It encodes that. So for Minkowski space and time that we are dealing with, instead, this will be, first of all, space-time independent. So this will be x independent, which means that it's flat, meaning nothing funny happens as you walk through the space and time, and you look exactly the same, identical. Okay, every point. And we will represent this with a quote, because one should be careful what can be represented as a matrix or not, but I'm being naive here. We will use 1, -1, -1, -1. This is a 4x4 matrix, and everything else is 0. Okay? So sometimes this is called the Western convention. Another often used convention, again, this is what? -1 + 1 + 1 + 1. Related by minus sign. Okay? Particle physicists use more of this convention because they're going to stick to the coordination. They're not going to get out of the coordination and just fix it. More formal theory and gravitational people would prefer this convention because if you start adding more dimensions, okay, I want to explore 5D. I want to explore over 6D. Keep going, 10D, 2060. Then, right? You add a +1, right? And things doesn't change much. Here, you radically change in the sense that, oh, now determine the flip plus minus, crazy as that, right? So in that sense, those people who will take this as a better convention, if you designate your life and devote your life to the body, I'm not one of them, actually, right? Sometimes people stick to that. And because of that, there is an insane amount of confusion in the literature, right? Or which sign is correct and which convention are you? That's part of life. If you decide to pursue this career, and I can rescue that. I can rescue from that problem, but I am still dealing with that problem, and I cannot help. So anyway, we're gonna stick to this convention for this lecture. And I cannot guarantee that I will be consistent either. So maybe I change my mind in the middle. We'll see. Okay, so here we are taking Minkowski metric, and this is represented as a 4x4 matrix like this. But some of the more mathematically inclined people, what do you mean? Is that a tensor or not? What can be represented as a matrix versus not? There's that question. Okay, so if you're bothered by that, I mean diagonal component of 1 -1 -1 -1. That's right. Okay, so like I said, this includes the local geometry. But for Minkowski space and time, this is completely flat in the sense that the metric is a constant value. Now, why this is useful? So once we have that, then we can define inner product. So suppose I'm given 2 4 vectors of this kind, either position vector or momentum vector, doesn't matter. Suppose I'm given 2 4 vectors. Then metric, now if I have it, allows me to define inner product. So inner product, for instance, I can use this notation if you like, can be defined as contraction of 2 4 vectors with a metric. So if this comes to you as a bit mysterious, let's remind ourselves in Euclidean. Euclidean inner product. So there, how would you do that? Well, I wanted to define Euclidean inner product in the high school sense. Well, x1, y1 plus x2 and very good 3. And I can write this as like g ij xi yj, where now my gij is just the +1 +1 +1, right? So once you define what your metric is, you can define your inner product in the language. That's all I'm doing. And in this sense, now you see that basically I'm treating spatial part is basically Euclidean, right? But I have this 20 minus sign such that I can differentiate. I do in my formalism, there's a way to differentiate between time component and the spatial component because of this over minus. Okay? So in component, this will be x0, by 0 minus basically Euclidean version of the product. And this minus sign tells me that this is time and this is the spatial component. Otherwise, it's basically same. Okay, so once I have an inner product, then what we can do is that we can now I don't know whether some of you who actually studied the QFT at least once before had a similar experience. In my case, when I was first studying quantum field theory in graduate school, at least the first few months, it was all about, can I do this tensor calculation correctly? Okay, no room for actual concept. I remember I was busy with, can I deal with this computation? Like lower epsilon tensor, oh my God, I'm breaking down, right? I'm just busy with the metric tensor. If somebody throw me extra epsilon tensor, I'm gone, I'm doomed, right? It was just busy with that. But you have to take that time and you have just to do practice. Okay, you just do enough exercises and computations that you build your confidence that I know this. Okay, so I'm slowly introducing all of that, at least necessary for follow the lecture. But it's part of the language, being familiar with language, and then more physics will come. Okay, so what is the raising and lowering index? So given a 4-vector with upper index, sometimes called I don't know if it still does people, contravariant vector. And then there's another object with a lower index is called covariant. But name is name. Just one is up, the other is down. That's all. But if you are given a metric tensor, you can, starting from if you like, contravariant vector, you can construct a covariant vector and vice versa. And you know how to do it. Okay, so let's be totally explicit. So if this were in an upper sense, were x0, x1, x2, x3, obviously, given a Minkowski metric with the specification of the convention, you can explicitly compute it, right? So time component has been lowered. You literally just do the computation, right? And then, 0, minus 1, minus x2, minus x3. These are just numbers, right? It's just number. And it's just that the spatial component got flipped. Minus that. That's all. And then there's also, this is lowering. Now, sorry, this is, yes, lowering. And then in order to define a raising indices, we have to define an inverse metric. So given that Minkowski metric, inverse metric will look like the upper index, such that, by definition, if I had a alpha nu, that was original my metric, and then if I multiply alpha mu, so here the repeated index are summed over. This is called the Einstein summation convention. Okay? So if you want me to do it explicitly, what I mean is that alpha is summed from 0 to 3. That's what I'm saying. And then alpha nu. And then this, by definition of being an inverse metric, is delta. Another way of writing this could be just G inverse G is 1. I'm just writing an index. Okay. And in metrics, you can get what this should be. Well, I'm taking this matrix representation, and which matrix I have to multiply to get identity 4x4 matrix. Well, that's already 1. So 1 is good to keep to be 1. Minus 1, I can just multiply by minus 6. So in matrix representation, again, this will still be only the diagonal entry with the 1, minus 1, minus 1, minus 2. Okay? But now it's good to have the inverse metric. Well, I mean, it's always good to have inverse object, because now I can define raising indices. So given covariant vector. Now I can construct a contravariant vector if I have a inverse vector. So I can freely raise lower indices using that, which is generally true. But in particular, if you make Minkowski visit type, we can do that. All right, so that allows me first define it in a product, and then I can basically go back and forth between up and down in this. And then what you do? Once you have these objects, the next thing you do is to define distance. Because now you have inner product, you can define norm. Any questions so far? How we can define distance? So given x and y, so let's say I just construct one difference vector. Yes.
I'm not sure that is the real inner product. Wait.
Yes.
Yeah. For x. X dot the wait.
Degeneracy is that pointed out.
Yeah. Usual inner product requires that the side of normal vector will be non-zero.
Yes. Okay.
But I'm not sure that.
Yeah. Good. Sorry. What he's trying to say is that if you recall from linear algebra, actual mathematical definition of inner product should not suffer from the degeneracy issue. Meaning, if the norm is zero, the vector has to be zero. So in spatial relativity, because of this funny minus sign, which I chose, because of this funny minus sign that deals temporal part and spatial time separately, you can have a zero norm, which will play extremely important role in the rest of the lecture, even if the vector is not zero. Okay, so whenever you hear, there's always physicist imprecise incarnation of the notion. But yes, you're right technically that this thing has a degeneracy issue, but precisely designed such that degeneracy always occur for what is known as like vectors. And then we know what that means, and that plays an absolute central role in the rest of the discussion. Thanks for pointing out. Any other questions?
Every GNU in this class are only diagonality.
Yeah, throughout this lecture and next semester lecture, yes, we will stick to the metric, which is basically it's diagonal with the 1 and the -1 rest. Yes. Any other questions? Okay. So let's talk about distance, modulo that degeneracy issue. So given this, we can define distance this way. By the way, this does mean that x mu minus 1 mu. Okay? And this, we learned that we can write it as g mu. Okay, get this. So when I say distance, okay, it's not just Euclidean notion of actual distance. This is, if you wish, length of a 4 vector. And 4 vector has a funny structure. Okay? So for instance, remember, if I have x with that component, I have written here, so let's just use it. For instance, if I compute the x mu using the that method that I had written, you will get x0 squared minus x dot x. Okay, so if I just rewrite the three component as an x vector, that's the distance, right? And unlike in the Euclidean inner product sense, where this is 0 means that the vector itself is 0, right? But this doesn't satisfy that because there's a difference between the two. Okay, that's why you can get funny structure that even for non-trivial vectors, you can get 0 norm. And again, they will play the crucial role. Now we can talk about infinitesimal distance, which we will denote it as. So I will introduce a small displacement, small dx mu, and then out of that we will construct a small displacement or small distance, infinitesimal distance, by contracting that with the metric. Then we are going to use that. We're going to denote it as a ds squared. That's a line segment in this particular geometry. Once again. Okay, so that's basic notion that I needed to introduce isometry. Okay, so I think now I have at least minimal amount of ingredient to introduce isometry of this space and time. So iso means not changing. Metry here means metric. So I'm looking for basically space-time transformations that the metric invariant. So what is the logic here? Not much of logic. So you're given a background space and time that you are given to play with, and then you're asking, what are the set of transformations you can do that doesn't change the metric of that space and time, right? So one way to read off that is that, say, starting from the line segment, because we can extract the finite transformation once I understand how things act on the infinitesimal segment. So let's take an infinitesimal segment, and then you're asking, can I do a transformation such that it doesn't change this line segment? Right, so this equality is the notion of isometry, and which I will make much more explicit. So let's try to do it. So starting from a component coordinate, if you wish, suppose I do make a transformation of that sense where this is certain 4x4 matrix. Okay, so this has a core component. You're doing literally matrix multiplication on that four column vector x2. Okay, and then the question is, what structural constraint this capital lambda meaning has to satisfy in order for this to be true? So at this point, I'm just doing random arbitrary 4x4 matrix, right? So let's read off structural constraint on this transformation matrix that satisfies this. Okay, so therefore, let's just write it out. So S prime square is, by definition, G mu dx prime nu plus prime nu. Okay, so first I just have written down the definition. Now, from this, you know that infinitesimal version is either dx prime nu prime. Dx nu is lambda nu, right? So I can rewrite this as G mu nu, and then nu alpha, say, nu beta, dx alpha, dx beta. So, and this is good to be called line segment in original x basis. So this is what you might call a transformed metric, right? Therefore, the statement of this now demanding that this should be equal to original line segment, the definition of isometry, means that it should be, let me just pick alpha beta combination. It has to satisfy this. So from this, we can read off, so given a metric, the constraint on the structure of isometry is that G alpha beta should be equal to lambda mu alpha mu beta G mu. So given this metric, say tensor, if you perform Lorentz transformation, or transformation for now, and you should go back to the original metric. So that's the definition of isometry. So we will develop one by one. Okay, so that's the set of transformation I'm looking for. So that's the set of isometry that I'm looking for. But we will develop more. But for now, we can immediately understand the following fact. So for any such transformation, that leaves this version of say equals in a product invariant, right? So if I do lambda transformation, that's still a dot b dot is still the same. Okay, it doesn't change notion of in a product, and therefore notion of angle in this we are four-dimensional space and time, not just clean Minkowski, clean Euclidean. That's it. So it preserves in a product, obviously. So because in the sense you can say that I wanted to look for transformation of that sort, but if you have a transformation that lives in a product invariant in this sense, then obviously it also preserves the norm. Basically here I was using preservation of the norm. Good. It turns out that this set of transformations so set of isometry of that kind, lambda mu. Okay, so now if this is a mere collection of all those things, forms of group. So there's a name for that for now. So that group is called the Lorentz group. Well, for some of you, what is group? Here, I don't have time to actually go through the group theory thing. Group means that there's a set of elements, say A, group. Here I'm just explaining this. I'm just not even explaining, I'm just telling you the definition. Group is a set of elements, okay? Such that it satisfies there exists always identity object. Identity object means that if you multiply that on any object, it returns back for any object of the group G. So suppose let me just call this group the set to be G. And then for any element A and B in G, the product of the two should be part of the group itself. So if you do the whatever the group multiplication, should be closed. The first, for any element of G, there should exist inverse object such that A inverse is okay. So I'm not being super careful about like left multiplication, right multiplication. I'm being sort of sloppy, but I'm just telling you the basic definition and notion of that. And finally, there's notion of associativity. So which means that if I pick three elements, so if I pick A, B, C of the group, then this notion has to be fulfilled. Okay? So if you have a set of elements that satisfies that criteria, it's called the group. Obviously, understanding group theory itself requires full designated semester, at least, or even 1 year study. We don't have time to go through that, but I will tell you some basic structure of this part directly, okay, without going through the mathematical story behind it. So here, the claim that I made is that if we care about the Minkowski space and time, and then if I wanted to know the set of coordinate transformation that leaves metric invariant, so isometry, they form a certain structure called the group, Lorentz group, and then I will about to define a structure of that one.
That would be forward
Because I haven't introduced the translation yet.
but the isometry will be defined.
You're right, and I will also introduce that. But for now, in case you have noticed, I've been only strict myself to that particular transformation.
But you did not fix the origin.
True. So what I'm saying is, so given X in the slot notation, I only consider the homogeneous transformation. I have not discussed the possibility of the shift in the origin. And this will obviously promote Lorentz group into concurrent, which I will discuss. Good. Any other question? Okay. Okay, so let's understand the Lorentz group better. And in notation, this Lorentz group for now, there's a notation for that. It's called O3 homology. So let me explain. So for this, let's recall first known story. So let's talk about this ON. Right? So what was ON? ON was set of n by n matrix. I'm already speaking in a sense representation, but anyway, n by n matrices such that all those elements satisfy this knowledge. Okay, where this T is a transpose. And in case you remember, the context in which such an object arises when you had a Euclidean version of a n-dimensional space. If you had n-dimensional Euclidean space, by which now you can understand language is that basically 1, 1, 1, everything. Okay, so n-dimensional, and then you wanted to find a transformation that leaves inner product invariant. Okay, and those objects were such a matrix, so x stands to all times x with this orthogonality condition that satisfies that leaves this space in there, inner product invariant. Now, this is almost that. So 3 plus 1 is 4. Right? So we are almost dealing with all 4 symmetry here. However, because of the funny minus sign that in the metric of Minkowski that differentiate between the space and time, so 3 space 1 time, there's extra minus in between. So that generates extra sort of structure and then subtlety. Okay? And so this is basically adopted from this notation, but now carefully differentiating too. Good. So now let's explore actual structure of this. Okay. But any questions so far? Okay. Hold on. Is that clock meaningful?
If we have a cursor,
How meaningful that time is? Fully?
always turn.
Huh?
Always turn.
Well, okay. This is good to go. 10 more minutes. Okay, so at least I want to derive Lorentz algebra. Okay, so let's keep going. Now we can do. So what was the definition of elements of that? Let's just recall ourselves at first. This. So let's take a determinant of this expression. Okay. So roughly speaking, you have 3 matrices. 2 are the same. You took a determinant. So this tells us that determinant of lambda squared is 1. So please convince yourself. So this tells me the several things. First of all, the determinant of lambda itself, remember, we are dealing with R being real components. Okay, this is the real. I'm talking about 4x4 matrix with the real entries. Okay, why? You can ask yourself, why am I constraining myself to the real entries? I'm talking about 4 vectors which consist of a real component, right? And I want to do a transformation. I don't want to see imaginary part always turned up into, right? So I'm talking about real matrices. So that means that this cannot be 0. What it means is that there exists lambda inverse for all of those lambda matrices, which is better B, because I want to have a group. But I can understand more because this is a real. What it means is that the determinant of lambda is either plus or minus 2. Okay, it's not just non-zero. I know actually it should be either plus or minus 1. Okay, so we can branch into. We can consider plus 1 factor, minus 1 factor. And there's a name people likes to give a name. In math then, this corresponds to spatial orthogonal, right? SO. It's called proper. Pretty subjective name. And any guess for this part? Improper. Genes. Okay, it's called the proper sector, proper part subgroup. It turns out that the selection of element, group collection of element with the +1 determinant closes itself as a subgroup. Okay, so this form is subgroup. Okay, so then we will explore, and then we can do something more. So in this expression, we can zoom in to this 0, 0 component. Okay, and then 0, 0. And then this is summed over. So I can look at the 0, 0, I, where I is a spatial. Because this is the diagonal, I don't have to look at off diagonal choices of that. So that gives me the following. So 0, 0 square, because metric is a +1 there. And then lambda I 0 square. And then I look at the 0, 0 component, which is okay. So what that means is that 0, 0 square is equal to 1 plus square, but this is literally square of the real entry. This is greater or equal to 0, which means that the 0, 0 component is always greater or equal to 1. Okay? Now once again, that this allows us to branch into two pieces. Either 0, 0 component is equal to greater than +1 or -1. There's also a name. So this part is called Orthochronous. And this, whatever. Okay? Now, why this is called Orthochronous? In the following sense. Remember, what does lambda 0, 0 does? It takes a 0 component and turn it into new 0th component. Right? What was going forward in time versus before, what was a positive entry, it turns into the same positive entry. It doesn't flip the sign of 0th component of the 4 vector. So even if it was a time in the sense of x mu, it still goes into the positive time direction, right? Or if it was an energy in a momentum sense, it takes the energy of the previous component and turns into still positive energy component. Okay? So, which physically much more makes sense based on our daily lives. So, the statement therefore is the following: Lorentz group can be factorized into 4 sectors. Okay, and we're gonna zoom into the sector with these 2 properties, and then get the rest. I'm just gonna spend 3 more minutes or 2 more minutes maybe. And then we'll continue next time. So therefore, we will focus, select the sector with a permanent lambda in +1, then orthochronous. Okay, it turns out that collection of this alone form a subgroup. We can check, and also collection of this alone form a subgroup. So I can just choose both of them. It's called proper. Okay. So basically, yes, I'm just looking up one. Yes, okay. And then one can explore. Oh, let's see if I can do this. Maybe I can. Like that, right? So it turns out that then once you understand this, one crucial point here is that being improper, that means that any element is continuously connected to identity element. Because identity element have a determinant to 1. If you start out here, there's no way you could get there in a continuous manner. You have to flip discretely the sign. Okay? So this sector, therefore, is continuously connected to infinity, and we're gonna focus on here. And then, but you can get to other sectors by means of discrete transformations. Okay, so other sectors can be reached by either other sectors, either determinant to flipping, or 0,0 component flipping discrete transformations. And those are called parity and then time reversal transformations. And the parity is 1 minus 1 minus 1 minus. Basically, you flip on this spatial component to minus. Okay? And time reversal is only flipping temporal component or combination of these two. So you can just cover the rest once you understand this together with these discrete transformations. Okay, so time is up, so probably I have to stop here. Next time, we will derive further the actual mathematical structure, algebraic structure that Lorentz group has to satisfy. And then we will also include a translation on top of that to actually talk about full Poincare. Okay, so that's all for today. I will discuss next time. Thanks.